I want to follow up the last video on the Sn2 ring opening of this cyclohexene oxide because the way I explained it, it might have been a little non-intuitive because when we first learned about Sn2 and Sn1 reactions, we said, well, if you have an aprotic solvent with a okay leaving group, but a really good nucleophile, you'll have an Sn2 reaction. But if you have a protic solvent, with an excellent leaving group, excellent leaving group, and a weak nucleophile, that would lead you to an Sn1 reaction. And everything, all of the ingredients that I showed you in the last video, actually were more in this direction. This was actually an acid catalyzed reaction, so it was definitely protic. And then this ring is strained right here, this epoxide ring, and we already protonated this oxygen, so it was a good leaving group. And clearly, the water is, the H2O right here, is a weak nucleophile. So if we just went off of the checklist that we learned about when we just explored the differences between Sn1 and Sn2 reactions, we probably would have predicted an Sn1 reaction here. We probably would have said the first step would have been that this bond just broke on its own, and this guy just left, forming a carbocation, and only then would the water, the weak nucleophile, would have attacked the carbon. And in that case, it could have attacked from either side, because all of a sudden it would lose its handedness, this carbon right here. But everything I've read, and I've actually never performed this reaction in a chemistry lab, but everything I've read says that this is the reaction that occurs, that you actually have this, I guess you could call it stereospecificity, that you only get the trans version is actually what predominates, and actually what is going on is an Sn2. So my best explanation is that this is really more of, you could call it an Sn2-like reaction, because it really meets the checklist more for an Sn1 in terms of what the reactions are. But because the end product is actually selective, you actually end up with the trans as opposed to both the cis and the trans, we're assuming that an Sn2 type of reaction must have occurred. But I really wanted to make this clear because it really kind of goes against the grain of our checklist of predicting whether an Sn1 or an Sn2 reaction would occur. And the reason why, at least in my mind, I think that the Sn1 reaction maybe didn't occur is, in order for it to occur, this carbocation needs to form. And that carbocation, it's secondary, it's not tertiary, so it's maybe just not quite stable enough. Now, Sn1 reactions can occur with epoxides, and I'll show you two examples. So if I have, let me draw two examples here. So this is ethane. If I just did a double bond here, it would be ethene. But if I have these bonded to an oxygen, this is ethylene. This is ethylene oxide. And once again, if this was an alkene, it would be called either ethene. That's actually the official name, but some people call it ethylene. And so the common name for this is ethylene. Actually, I spelled it wrong. It's ethylene, not with the ethylene oxide. I've even seen on the web a couple of times people call this ethene oxide, which in some ways would be more consistent. So let's say on one hand we have ethene oxide, and let's say on the other hand, we have something that looks like this. Let me try my best to draw it. We have something that looks like this. And so this part, if we just look at the main chain, you could either view this as a propane, or use having 3 carbons, 1, 2, 3, and then a methyl breaking off of it. But this Y shape, where you have 4 carbons here, is usually called isobutyl. So you could call this isobutylene oxide. So let's call this isobutylene oxide. That's what you're more likely to see. Isobutylene oxide. And remember, they just pretend like this is a double bond. That's where you get the isobutylene oxide. But then to make it clear that it's really not a double bond, that there's really an oxygen in there, it's really not an alkene, you put the oxide there. Now let's think about the different reactions that might occur if we have a nucleophile in either situation. So if we have a nucleophile, over here, for the ethylene oxide, either of these carbons are primary carbons. So if you have a carbon right here, let me draw all of its bonds. It's bonded to one other carbon. It's bonded to a hydrogen and another hydrogen right there. So it's a primary carbon. It would not be a stable carbocation. So in this case, you would definitely predict that an Sn2 reaction would have to occur with this epoxide. That the nucleophile would attack back here, and then this electron would be taken back by the oxygen, and that would open the ring. So this would be an Sn2 situation, and in my mind this is pretty clear. But in this situation, you do have a primary carbon right here. It's only bonded to one other carbon. But over here, right over here, you have a tertiary carbon. It's bonded to 1, 2, 3 carbons. So this would be a stable carbocation. So in this circumstance, you would actually expect that this epoxide ring is so strained that the first step is that the oxygen would just take the electron. The oxygen would just take the electron, and then you're left with something that looks like this. Let me do it in the same colors so it's clear. You would be left with something that looks like this. And now, since it took the electron just like that, or actually, maybe let me take a step back. It has to be a very good leaving group. So it wouldn't necessarily just take the electron right there. The first step in order to make this a good leaving group would be if you maybe had a water around, or something that it could take or some type of acid that it could take a hydrogen proton from. So the first step is it would take a hydrogen proton. Let me do this a little bit neater. It would take a hydrogen proton, so it would give an electron to a hydrogen proton so that it becomes a good leaving group. So now our molecule looks like this. Do it in the same colors. Our molecule will look like that. That's our carbon. And now this is an oxygen bonded to a hydrogen. And now this has a positive charge. This is now will just be a water. I won't draw it anymore. And now this is an excellent leaving group, tertiary carbon. This is classic Sn1. Classic Sn1 reaction. So this guy can essentially leave, and then we are left with down here. Let me draw it over here. We are left with something that'll look like this. We have our carbon bonded not to hydrogens, to other carbons. So these are carbons over here. And then this carbon is bonded to this OH. We now have an alcohol. And this is now a carbocation. And now this is ready to be attacked by even a weak nucleophile. Even a weak nucleophile could attack this. So when you have a tertiary carbon in your epoxide ring, look for an Sn1 reaction. But if you have anything less, as far as I can tell, based on the reactions that I've looked at in multiple books, if you have secondary or primary carbons, it seems like Sn2 is going to be more likely to break your epoxide ring.